A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Today we are going to talk about carbon nanotube. This is really vast topic, so we need to divide it into two parts. The first part we will discuss it today, and the next part we will discuss in the next lecture. So this is actually the part of nanophysics and technology course outline, and having the course code of PHY445. Carbon is present in the periodic table in the group of non-metal regions, and it has the atomic number of 6 with the atomic weight of 12.01, and it is represented with the symbol C. So first we look toward the carbon. What is this? What's this element have? The number of electron and the number of proton and its isotope, before going towards the detail of its extraordinary property which it have due to its unique morphology. So isotopes are actually the atoms of the same elements having same number of protons while different number of neutrons. So the carbon carry 3 different isotopes. One is carbon 12, the other is carbon 13, and the third one is the carbon 14. But the stable carbon 12 and carbon 13 are the stable configuration, while the carbon 14 is unstable and it is actually radioactive. It's not stable. Actually, the colors of the different elementary particle, the particle inside the nucleus, is represented by their respective particle. Just like this is proton, this is neutron, and this is electron revolving around the nucleus. So we need to compare the different type of bonding before going toward the detail of carbons, because carbon carry covalent bonding, and before discussing the covalent bonding in detail we need to know the different type of bonding. We also know from elementary classes about ionic bonding, covalent bonding, and metallic bonding, but this is a brief description about it. In case of ionic bonding, ions transfer from one atoms toward another atom, and as a result they bond with each other. Just like the simple example is the sodium chloride, where sodium donates the electron and chlorine gets the electron. As a result, sodium carry positive charge while chlorine carry negative charge, and it forms the ionic bonding. The second type of bonding is the covalent bonding, where they share electron with each other. Just like in case of chlorine and bromine here in this case, depending on the number of electron, it is further divided into 3 categories: whether they form single covalent bond by sharing 1 electron with each other, or whether they form double covalent bonding by sharing 2 electrons with each other, and the third case is sharing 3 electrons with each other forms the triple covalent bonding. And the third case of the different type of bonding is the metallic bonding, where metallic bonding occurs between the ions and the electron. Electrons are present inside the metal, and it can move easily inside the metal, and but it cannot leave the metal by itself. If you want an electron to leave the metal, we need to provide an amount of energy that is actually called as a work function. But in this case, in metallic bonding, they are bound with each other, and as a result we have metallic bonding for some materials. So looking towards the covalent bonding, we have one, just like if we consider 2 atoms, one is represented by A, another represented by B. So one A can also share 1 electron, and B can also share 1 electron, and they are paired with each other. If we compare the double and single covalent bonding, then in case of single covalent bonding, only 1 pair of electron holding the nuclei together, while in case of double covalent bonding, 2 pair of electron hold the nuclei tighter and closer together. The covalent bonding is further simplified and understandable from the periodic table, that which element will form the covalent bonding. Just like looking toward the periodic table, you can consider those elements whose outermost shell is partially filled, just like looking toward the H2 is forming the covalent bonding. Or H2O, they are also have covalent bonding. So similarly, in case of we have different semiconductor material, just like silicon carbide, formed by the combination of silicon and carbon. And similarly, gallium arsenide, just like which is made by the combination of gallium and NaS. So that is a type of different covalent bonding, and the basic criteria for the covalent bonding is that have partially filled outermost shells. But in case of ionic, it have only 1 or 2 electron extra, or 1 or 2 electron needed for completing its outermost shells. So this is something about the covalent bonding. So we are going to introduce the carbon nanotubes that is formed from the carbon, and it is actually the allotropes of carbon with a cylindrical nanostructure and unique nanostructure. Their properties are valuable for nanotechnology, electronic optics, another field of material science and technology, and it carry extraordinary property. They also possess thermal conductivity, mechanical and electrical properties, and their name is derived from their long halo structure with the walls formed by the 1 atom thick sheet of carbon called as graphene. So moreover, these sheets are rolled at specific and discrete angles. So multi-wall carbon nanotubes consist of multi-roll layer that are concentric tubes of graphite, and basically we have in this case we can basically discuss the introduction part of the carbon nanotubes. So this is actually the structure of carbon nanotube, how we can make these specific structure of these carbon nanotubes, and so it can represented by different type of coordination vectors. So this is a basic one-dimensional crystal structure of the carbon nanotubes. So it can be represented by 2 vectors, that is A1 and A2. So we have a carbon nanotube that is characterized by their vector, that is A1 and A2, and have a specific angle. So this is some particular shapes of the carbon nanotubes, which seems very interesting, just like armchair and zigzag and channel, and we have the particular value for that. Just like for the armchair we have n is equal to m, and for zigzag we have n is equal to 0, m is not equal to 0, and for chiral we have both n and m not equal to 0. So this is multi-wall carbon nanotube, the structure of a multi-wall carbon nanotube, and it's looking amazing, and the atoms are arranged in a very regular pattern. So we can classify the carbon nanotube into different types. So there are several parameters that characterize the nanostructure, which includes but not limited to the hybridization and the different other parameters, just like we have graphene or graphite, and its dimension, just like we have 1 dimension, 2 dimension, and it also depends upon its length and width and thickness of that particular carbon nanotubes. So it's have very interesting application. The applications are only due to its interesting property. The first one is that it has structural property, and basically it is used in many structural property, because many structure have been proposed, ranging from everyday item like clothes to and sports gear to combat jackets and space elevators. So it has also interesting application in electrical circuits. So it has electrical property, interesting electrical property, that is this last structure of carbon nanotube can be used for thermal management of electronic structures, and it is used for electric cables and wires for carrying electrical current, may be fabricated from pure nanotubes and nanotube polymer composites. So it's a paper batteries, a battery engineer to use a proper paper thin sheet of cellulose. So the nanotubes act as electrodes, allowing the storage device to conduct electricity. So it has further application in solar cells. Solar cells are developed from the carbon nanotube by using a carbon nanotube complex formed by the mixture of carbon nanotubes and a carbon buckyballs. So that is also specially known as fluorines. So we have ultra capacitor that was developed in America in MIT lab for electromagnetic and electronic system using nanotubes to improve the ultra capacitors. It is also used, the carbon nanotubes are also used in various medical applications because of its extraordinary properties. So we are dividing carbon nanotube into several types. So one is the graphite, and graphite has some of the property and some of the structures, basic structure, due to which it has interesting property. So here we are looking towards the structure and its properties as well. So we have soft, and the graphite is actually soft and slippery. So many strong covalent bonds holding the structure together, but only in 2 dimensions. So the layers are free to slide easily over one another. So graphite powder is used as a lubricant. So similarly, it has brittle nature. All the bonds are directional within a layer, and stress across a layer will tend to break them. So graphite rods used for electrolysis easily break when dropped. It is electrical conductor. Only 3 of the valence electrons are used in the sigma bonding. So the other electron is in p orbital, which can overlap laterally with neighboring p orbitals, making gain molecular pi orbitals that extend over the all of each layer. Electrons are free to move within these delocalized pi orbitals. So it is insoluble in water. There are only very weak van der Waals attraction between the carbon atom and the water molecules, whereas the carbon atoms are bonding very tightly to one another. So it has very high melting point. Many strong covalent bonds holding the layers together. It requires massive amounts of energy to pull it apart. So we have diamond, that is other form of carbon, and it has very interesting property. This is actually this structure of diamond. And looking toward the properties and application, it is actually hard, and many strong covalent bonds are holding the structure together. Along with hardness, has also brittle nature. So all of the bonds are directional, and stress will tend to break the structure in a malleable substance, such as for example a metal. The bonding is non-directional and can still act if the particles are displaced with respect to one another. So it is insulator. All of the valence or outer electrons are used in bonding. So the bonding are sigma, and the electrons are located between the 2 carbon nuclei being bound together. So none of the electrons are free to move. It is actually insoluble in water. So there are only very weak van der Waals attraction between the carbon atoms and the water molecules, whereas the carbon atoms are bonded very tightly to one another. So very high melting point, many strong covalent bonds holding this structure together. So it requires massive amount of energy to pull it apart. And we have nanocarbons. So the nanocarbon has properties and application in electrical application, mechanical properties of interesting, and thermal properties and storage properties. So these are some of the examples of nanocarbons. Fluorine is also an example of carbon specific structure that is discovered in 1985. Because of its unique structure, it is widely investigated and has wide range of applications. We has Buckyballs structure for the carbon nanotubes, and this Buckyballs structure is a really interesting arrangement of atoms, just like a football. You are looking that it has very symmetric shape, and it is lubricant. If we see, it has very large surface area. Normally surface area is a very important factors in determining the property of the nanomaterials. Just like if we see for the bulk material, the number of atoms that are located in the bulk are greater compared to the atoms that are located in a surface. But if we are looking toward the nanomaterials, here the number of atoms present at the surface increases greatly compared to the number present at the bulk. So this greatly change the property of that materials, because the nature or behavior of the atom present at the surface are very different from the atoms present at the bulk. So it's a large surface area, and that is why it is used as a catalyst. It has high temperatures just like it has high pressure and hollow structure that is used for catching particles. So we have buckyball structure that is really like football shape, and it forms a crystal by weak van der Waals forces, and it is used in superconductivity because we have some of the material just like K3C60 is superconductor at 19.2 K, and we have some other structure that is made from RBCS2C60 that has the comparatively high transition temperature that is 33 K. So buckyballs is the specific arrangement of atom in the buckyball. So this is formed by a crystal by weak van der Waals force that has a superconductivity. We discussed in the last slide. So this is the property of the buckyballs. So it is soft and slippery. So few covalent bond holds the molecules together, but only weak van der Waals forces between the molecules is present. It has brittle nature. If we look toward the mechanical property, it has brittle nature. It is soft, weak crystals typical of covalent substance. So it is actually electrical insulator. So no movement of electron available from one molecule to the next. So this exception could be the formation of nanotubes that are capable of conducting electricity along their length. So these are the subject of some experiment in microelectronics. So it is actually insoluble in water. So there are only very weak van der Waals attraction between the carbon atom and the water molecules, whereas the carbon atoms are bonding very tightly to one another in the molecules. So it has very low melting points. So it is low melting point solid. So it's typical of the covalent crystal where only van der Waals interaction have to be broken for meltings. So this is some of the property of the buckyball that is widely used and investigated, and it has wide range of application. So the structure is very similar to the football, and it is arranged in very regular shapes and arranging themselves, and that particular regular shapes increases properties. Especially it is used in an application where we need high surface area. So that is specifically used in catalysis. So because of its high surface area and the high ratio to the surface to volume, surface to the bulk atoms ratio, so that is interesting. So it is widely used in such type of material. This is buckyballs as special. So if you look toward the diamond, actually the nature of atoms is same. Looking toward the diamond are the buckyballs, are the fluorines, are this the buckyball structure of the atoms. The nature of atoms is same, but they are only different by the arrangement and that completely change the property. Just like if you see, diamond is insulator because of the valence electrons are used in bonding. But if you look toward the graphite, it is electrical conductor because only 3 of the valence electrons are used in the sigma bonding. So the graphite and bonding have very different property from each other. The graphite is electrical conductor and it is used in electrical conductor application. But the graphite, if you look toward the properties, graphite is insulator because the valence electrons are used in bonding, and that bonds are sigma and the electrons are located between the two. And coming toward the buckyball structures, so it is again electrical insulator because no movement of electron is available from one molecule to the next. So this exception could be the formation of nanotube and that are capable of conducting electricity along their length. So these are the subject to some experiment in microelectronics. So the properties are very differ from each other. Looking toward the diamond and graphite is differ from each other. So that is why it has interesting application that is used, and it is widely investigated in various type of applications. So similarly, looking toward the melting point, are the other properties just like mechanical property, the brittleness. Graphite is brittle in nature. Graphite is brittle and it can be broken without elastic deformation. And looking toward the diamond, it's again brittle. If you see the mechanical property, both the diamond and the graphite carry the same mechanical property. Both are brittle with each brittle. And looking toward the buckyballs, so it is also again brittle because it's perform no elastic deformation. And so this is some comparison of their property with each other. Buckyball have low melting points, solid, And looking toward the diamond, it has very high melting point. So this is really interesting. Is so huge difference in melting point with each other. So and looking toward the graphite, it has also carry very high melting points. So these are some of the properties that are differ from each other due to their specific arrangement of atoms or their specific structure. So this is something about the carbon nanotube. I hope in next lecture we will also continue it and discuss part of that.